Next, we'll talk about solving exponential and logarithmic equations. The goal in this section is just to use all of the properties that we just talked about and the properties from the previous week to be able to isolate a variable in a certain equation. So in this case, we're not just going to be given an expression that we want to simplify. This time we'll be given a whole equation, and we're trying to solve for x. So as an example, let's look at 5 to the x plus 1 is equal to 5 to the 2x. So one way of approaching problems like this in this particular case is to notice that on the left side we have 5 to 1 power, and then on the right side we have 5 to another power. So what we can use is what's called the 1-to-1 property. And what that says is essentially that if you have 5 to 1 power matching 5 to another power, then the powers have to be the same. So this means that x plus 1 has to equal 2x, and then you can solve this for x. If you subtract x from both sides, you'll get that x is equal to 1. So that's one property that we can use. We discussed that early on with logarithms. However, I don't particularly like to use the 1-to-1 property explicitly. What I would prefer to do is something that you'll use more generally on these equations. So what I would do in this particular equation is I would say, notice that I have a 5 as an exponential base that I want to kill on both sides of this equation. So the way that I can kill an exponential base of 5 is by using its corresponding logarithm, which is log base 5. So the way that I would approach this is take log base 5 of both sides. In other words, log base 5 of the left side of the equation has to equal log base 5 of the right side of the equation, because those two sides were supposed to be balanced. But now I can use the inverse property to say that this log base 5 will cancel with the exponential base 5, same on this side, to get x plus 1 is equal to 2x. And that means, again, that x is equal to 1. So either way, you'll get to the same solution. Notice that the original method over here, the 1-to-1 property, is a little bit shorter, but I would prefer that you start thinking in terms of this left-hand side approach, because this left approach will work more generally, even whenever the bases on either sides don't match. So if I had a 5 to 1 power is equal to 10 to another power, then I wouldn't be able to use the 1-to-1 property. I would have to use the approach that I just talked you through. So let me give you another example of that. So let's say that you have 2 to the x minus 3 is equal to 5. We want to know what x needs to be in order to solve this equation. So what we could do is we could try first isolating any exponential term, which is what you'll do in general whenever you're trying to solve exponential equations. Try to isolate the term that you want first, and then you can worry about getting that x by itself. So what you could do is you could add 3 to both sides, and then you would have the new equation 2 to the x is equal to 8. And if you can just read off the answer from this stage, that's fine with me, but I would prefer that we did this in terms of logarithms. So if I wanted to kill this exponential base 2, I would need to apply the corresponding logarithm on both sides. So I would have log base 2 of the left side is equal to log base 2 of the right side. Now on the left side, because these are inverse functions, they'll cancel and I'll just get x. On the right side, I'm asking what exponent would you put on a 2 to get an 8? The exponent that you would put on a 2 to get an 8 is a 3. So we'll get that x equals 3 is the solution to this equation. So maybe before I move on, let me just point out that if you're trying to get a power by itself, so let's return to the example that we had up here. And maybe I'll do this in another color. So let's return to the example that we just talked through, where 5 to the x plus 1 is equal to 5 to the 2x. If our goal is just to get these exponents down, then we could also just use the power rule that we talked about in the previous section. And the way that we would do that is I can apply any logarithm that I want to both sides. So I could, maybe let's just take ln of both sides. Ln of the left side is equal to ln of the right side. So this is still a true equation. It might seem a little weird though, because ln and 5 to the whatever power, these are not inverse functions. So I can't just cancel them. However, what I can do is I can apply the power rule that we just talked about. So remember, the power rule allows you to take a power and set it on the outside of a logarithm. And I'll do that to both sides. So on the left side, I would get that x plus 1 times ln of 5 is equal to, if I bring down the power on the right side, it would be a 2x times an ln 5. And then next I could divide both sides by ln 5. Remember that ln 5 is just a number. So dividing by ln 5 on both sides, I would get that x plus 1 is equal to 2x, and that would lead us to the same solution, that x is equal to 1. So there might be several ways to approach any of these problems, but the thing that I want to emphasize is that if you're trying to get at an exponent, then it's a good idea to apply a logarithm to both sides of this equation. And the best choice for the logarithm to apply would be the actual inverse to the base that you're trying to kill here. So if you're trying to kill a 5 to the x, then you should apply a log base 5, because those are inverse functions. However, any logarithm will actually work. So it would be okay to just apply ln to both sides, because even if you just apply ln to both sides, that will still allow you to take these powers and set them in front, and then you'll have a linear equation rather than a logarithmic or exponential equation. Okay, so you'll see several examples involving these tools in the notes. I just want to make you aware early on that you can use several approaches in a lot of these problems, but I want you to start getting comfortable with the idea of either applying a logarithm to both sides of an equation or applying an exponential function to both sides of the equation, which is the next thing we're going to talk about. So, for example, in this equation, I'm not trying to kill an exponential base. This time I'm trying to kill a logarithm. So I don't like the fact that there are logarithms here. I would prefer if they were gone. Now here you can again use the one-to-one property. If you have ln of one number is equal to ln of another number, it is true that by the one-to-one property, I'll just say one-to-one property, the insides have to match. So x plus 1 would again equal 2x, and then therefore x is equal to 1. However, you can again think of this in terms of inverse functions if you want to, and that's sort of the way that I would prefer to think about it. So the way that I would approach this is I would say, okay, let's look at this. I have an ln that I would like to kill. So I want to get rid of this ln. The way to kill an ln is to apply its inverse function to both sides. And the inverse function of ln is e to the blah. So I should apply e to the left side, and that will equal e to the power of the right side. So notice that the function that I'm applying to both sides is e to the x, which is the inverse function of ln. So both of these sides are going to become exponents with a base e, because exponentiation with base e is the inverse to taking a logarithm, or I should say a natural logarithm. So now that I have both of these sides raised as exponents with the appropriate base, now I notice that because these are inverse functions, these things cancel, and they would leave me with just those powers. X plus 1 is equal to 2x. And now again, I can solve this to get that x is equal to 1. So I'm deliberately not varying the linear equation at all, because the linear equation itself is not the interesting part. The interesting part is just being able to get rid of logarithms or exponentials as we see fit by applying the appropriate inverse function. And sometimes you'll have to hold off a little bit before, sometimes you'll have to hold off a little bit before you are able to apply the inverse function that you want. For example, if I gave you this equation, here you would not want to exponentiate immediately because we don't have the ln term isolated. And because we don't have an ln by itself, we won't be able to use the inverse property that we've been using to kill that ln. So what we should do first in these examples is first isolate the exponential or logarithmic term that you need to isolate, usually the one that involves your variable. You want to get that by itself, and then you can apply the appropriate inverse function. So to isolate it, we would do what we normally do, when isolating expressions. So I'm going to add 2 to both sides here. That would tell me that ln of x is equal to 3. And now that we have an isolated ln, I want to get x by itself. To get x by itself, I can apply the inverse function to this ln to cancel it. And the inverse function of ln of x is e to the x. So I'm going to apply that to both sides. I'll get e to the left-hand side is equal to e to the right-hand side. Now notice I'm not multiplying by e. So this is not e times the left side equals e times the right side. What I'm doing is I'm taking the left side as my exponent with a base e, and that has to equal the right side raised as an exponent with base e. So I'm exponentiating with base e on both sides. Just like earlier, I took the logarithm of both sides. I'm not multiplying or dividing by something. I'm applying a function to both sides. In this case, the exponential function with base e. And the reason for doing that is that now on the left side, because those are inverse functions, they'll cancel and I'll just get x on the left side, and on the right side I'll get an e cubed. You can leave your answer like that, or you could plug this into a calculator to get a decimal approximation. But I'm happy with x equals e cubed. Now, there is something that we have to worry about when solving logarithmic equations in particular. Sometimes logarithmic equations will have negative answers that don't actually work in the original equations. So what we have to do is remember that ln of x has this domain. Sorry, that's a little sloppy. I'll say has domain equal to only the positive numbers. In other words, you're only allowed to plug in positives into a logarithm. So on these, you technically do need to be checking your answer to make sure that it doesn't cause any negatives inside of a logarithm. Here, e cubed is a positive number, so that's not going to be causing any negatives inside of a logarithm in the original equation. Similarly here, if I plugged in x equals 1 into the original equation, I would get a positive 2 on the inside of this, and a positive 2 on the inside of this one. And therefore, there wouldn't be any negatives on the inside of logarithms if I plugged in this solution. So it will be a valid solution. But sometimes you'll end up getting solutions here that would cause negatives inside of logarithms, and those should not count as actual solutions to the original equation, because you're not allowed to put negatives into logarithms. Notice that that problem does not occur whenever you talk about solving exponential equations like this one. That's because for exponential equations, you're allowed to plug in any x value you want. So exponential functions take as their domain any real number, or I should say all real numbers, whereas logarithms are a little pickier. For logarithms, you have to make sure that the inputs that you're plugging in are not causing any negatives.